In this video, we're going to learn about pH changes in titrations. Okay, before we can learn about pH changes in titration, we just need to revise some concepts. Now, earlier this year, we learned about conjugate acid-base pairs. So, for example, ammonia is a base. That's a base over here. It reacts with water to form the ammonium ion and the hydroxide ion. Now, in this reaction over here, ammonia is the base, and the ammonium ion is its conjugate acid. So to go from the base to the acid, what we do is we add H+. Okay? In this reaction, in this case, water acts as an acid. When it reacts with ammonia, it loses a H+ ion to form the conjugate base. Okay, so if that's the acid, this would be its conjugate base. So to go from acid to base, we lose H+. To go from base to acid, we gain H+. We've got another example over here. This is acetic acid. It also reacts with water to form the acetate ion and the hydronium ion. So in this case, this is the acid. We lose H+ to form its conjugate base. And this is a base in this case. And it picks up a H+ ion to form the conjugate acid on the other side. Okay. Now the other really important concept as well is that if we have a weak base, then its conjugate acid is a weak acid. Okay, so if we have a weak base such as ammonia, the ammonium ion is itself a weak acid. Now the strength of this acid is not quite as much as the strength of this base. So remember how we've got these equilibrium arrows. This reaction can go both ways. Okay, so we've got ammonia that can act as a base interacting with water, but the ammonium ion, if we put that in water, can also interact with water to some extent. On the other hand, if we've got a strong acid, like for example HCl, its conjugate base is going to be an extremely weak base that is not going to interact significantly with water. So in this case here, the reaction goes in this direction, but once we've got the chloride ions, they do not react with the water to any significant extent. Okay, so this is an extremely weak base in comparison to the strength of this acid over here. Okay, now moving on to pH changes in titration. The first example that we've got over here is a titration that involves a strong acid and a strong base. So in this case, we've got the acid that would be in the conical flask, and the sodium hydroxide is gradually added to the acid. We can see that the pH is increasing, which makes sense because we're adding a base. And what we can see is that there's a very typical shape for the pH curve, in that we see that the pH only increases by a tiny bit initially, and then there's a very steep part to the curve, and it flattens out again. And you'll notice when it's a strong acid and a strong base, the steep part of the curve is very long. And if we look at the midpoint of this steep part of the curve, we see that it corresponds to a pH of 7. Now, when we've got one of these graphs, we can work out the equivalence point by the titration by looking for the midpoint of that steep part of the curve. Okay, so at the equivalence point, we've got exactly the right volume of base to completely react with the acid, so neither reagent is in excess. So what that means is that at the equivalence point, the only substances that are in the flask are water and the salt that's produced in the reaction. So that's the example that I've got over here. So that corresponds to the curve that was on the previous slide. In this case, we've got sodium hydroxide reacting with hydrochloric acid to form sodium chloride and water. Now, if we put sodium chloride in water, it's going to break up into sodium ions and chloride ions. And neither of those ions are going to react with water to any significant extent to produce either hydroxide ions or hydronium ions. So that's why that salt is actually neutral. So if we add sodium chloride to water, the pH will be 7. Okay, the situation is quite different when we've got a titration which involves a strong base and a weak acid. You can see once again a graph has been plotted to show how the pH changes as the acid is being added. We can see the pH is decreasing, which makes sense because we're adding an acid. But what we can see is that if we once again look for the steep part of the curve and we find the midpoint of the steep part of the curve, that corresponds to the equivalence point. And we can see that the pH is now significantly greater than 7. So let's have a look at why that happens. Okay, once again, at the equivalence point, we've got exactly the right number of moles of acid and base to completely react with each other. Neither reagent is in excess. So what that means is that we've only got water and a salt that are left behind. But this time the salt is not neutral. So an example of this would be the reaction between acetic acid and sodium hydroxide. And in this case, the salt that's formed is sodium acetate. And we can see, so that's sodium acetate over here. Now, sodium acetate that ionizes to form sodium ions and acetate ions. The sodium ions are not going to interact with water in any significant ways to produce either hydroxide or hydronium ions. So that's not going to affect the pH. But the acetate ions in water, it reacts with the water. And in this case, the acetate ion picks up a hydrogen ion from the water to produce acetic acid molecules and hydroxide ions. And we can see we've definitely got some hydroxide ions being produced, and that's why this particular salt has a basic pH. The next slide shows us what happens when we've got a titration that involves a weak base and a strong acid. Okay, now again, we've got a steep part to the curve. If we find the midpoint of the curve, we can read off the equivalence point. And we can also see that the pH is significantly less than 7 at the equivalence point. Now, in this case, again, at the equivalence point, we've only got the salt and the water that are left in the flask, but the salt is acidic. Now, let's have a look at an example over here. In this case, we've got an example where we've got ammonia that is reacting with hydrochloric acid to form ammonium chloride. Now, that's one way we can write the reaction. If you're a bit worried about the fact that we don't have any water produced, another way of writing it is shown here. Okay, because ammonia, when you put that in water, it forms ammonium hydroxide anyway. So when ammonium hydroxide reacts with hydrochloric acid, it forms ammonium chloride and water. And an ammonium chloride, when you put that in water, again it ionizes. It produces ammonium ions and chloride ions. The chloride ions don't react with the water in any significant ways, but the ammonium ions, on the other hand, ammonium ions are the conjugate of a weak base, so they are themselves a weak acid. And so when you put ammonium ions in water, they're going to react with the water to form ammonia molecules and the hydronium ion. And you can see because the hydronium ion is being produced, that is why the pH is less than 7. Now, before we move on to talking about indicators, whenever we do a titration, we always need to make sure that one of the reagents is a strong acid or base. So let's say, for example, you were trying to do a titration involving citric acid, which is a weak acid. The other substance that you would need to use would have to be a strong base. And you can see in this graph why it doesn't work. The problem is we just simply don't get a steep part to the curve. And so, like this bit over here is just not steep at all. So it makes it very difficult to determine the equivalence point accurately. Okay, now moving on to indicators. So when we do a titration, it's really important that we choose the correct indicator. An important term that we need to be aware of is the end point of the titration. The end point is the point at which the indicator changes color. Okay? Now, different indicators change color at different pH levels. So each indicator has got what's called a pH range. That's the range over which it changes color. So in this diagram over here, we can see, for example, that litmus changes color in the range 5 to 8. So it starts to change color about here, and by the time we get to here, it's completely changed color. So what we need to be careful about is that we need to choose an indicator which changes color as close as possible to the equivalence point. So in other words, the end point must match the equivalent point. Okay, let's say we carry out a titration involving acetic acid and sodium hydroxide. That's an example of a weak acid with a strong base. Now, if we use the indicator methyl orange, the problem with that is that the indicator may just simply never change color. The pH is going to drop, but it's not actually going to drop significantly enough to cause a color change in the indicator. So that indicator just wouldn't work. On the other hand, if we choose phenolphthalein, that's going to change color at about pH 8 or 9. And that's ideal for this titration because that matches the equivalence point of the titration. Okay, on this slide here, we've got two other examples. The first example here is a strong acid versus a weak base. Now, if we're using a strong acid versus a weak base, The equivalence point is around here, okay, so at a pH of about 5 or thereabouts. If we use phenolphthalein, the colour change is going to happen way too quickly, okay. The colour change is going to happen by the time we've added this much acid, the colour's already going to have changed, right? And we haven't reached the equivalence point yet. If we use methyl orange, on the other hand, that's going to change colour around the equivalence point. So the end point is going to match the equivalence point. So that's the right indicator for this titration over here. Now you might be wondering what happens if we've got a strong acid and a strong base. Well, in that case, the steep part of the curve is so steep, the change in pH is so dramatic near the equivalence point, that it actually doesn't really matter in this case which indicator we choose. So phenolphthalein will work, methyl orange will work, litmus changes colour about pH 7, that will work as well. Okay, so quite a few different indicators will work. The only type of indicator that wouldn't work is, let's say you had an indicator that changes colour about pH 13, that wouldn't work, or one that changes colour about pH 1, again that wouldn't work. Now a lot of the time we're going to choose phenolphthalein for titrations that involve a strong acid with a strong base, because the colour change is so easy to distinguish. We're going from clear to pink, which is a very easy colour change to identify, whereas some of the other indicators, the colour change is less obvious. Okay, that's pretty much all we need to learn about pH changes in titrations. And now it's over to you to have a go at some of the questions about this concept that are in your OneNote.